Okay, everyone. We're gonna start in 1 minute. This is the second parallel session, the electrocatalysis session. I'm Iris. I'm the chair of this session. So our first speaker will be Dima from Weizmann Institute. Each speaker will have 15 minutes plus 5 minutes for questions. I will announce you 2 minutes ahead of time. Sticking to the schedule is very important. And please ask questions after Dima speaks by raising your hand. Okay, so Dima, you already shared the presentation and you can start.
Thank you. Thank you and good morning. Thank you for the organization of this conference. I will present you today my project about molecular and organic electrocatalysts for the reversible reduction of carbon dioxide as functional models of carbon monoxide dehydrogenase enzymes. So we all know that since the Industrial Revolution, the emission of carbon dioxide in the atmosphere is rising, and therefore the concentration of carbon dioxide is increased. So scientists during the years thought about to reduce the amount of carbon dioxide by using chemical and electrochemical reduction method in order to convert carbon dioxide to CO, carbon monoxide, and after that by using Fischer-Tropsch process to get C1 and C2 products such as ethanol or methanol. But there are two challenges for that. The first one that is to do the first process much efficient in order to get the products. And the other challenge is to move from the carbon dioxide directly to the products without having CO in the atmosphere. That's mean to produce CO in situ experimentally. So if we look to the carbon dioxide molecule, we can say that carbon dioxide is a non-polar linear molecule with a pair of short bonds of 1.16 angstrom. And if we add catalyst, there is electron transfer between the metal of the catalyst forward the carbon of carbon dioxide, and then the electrons will move to the LUMUS orbitals, and that result increasing of CO bond length that induce the bend geometry of CO2 and let us cleavage this molecule and get another products. So if we go to the non-reduction table of carbon dioxide, you can see that in order to reduce the first electron, we need a lot of energy. It's so stable thermodynamically. But after we reduce the first electron, we got the bend geometry, and then we can get the different products. So if we look now to the proton-coupled electron transfer reactions, you can see that it's much more stable thermodynamically, but the problem here that this reactions is so slow. So we need catalyst in order to achieve the different products. In our lab, we use unique family of catalysts that's called polyoxometalates. And what is polyoxometalates? Polyoxometalates are polyanion metal oxoclusters composed of early transition metals in their highest oxidation state, tungsten or molybdenum. So here we have an example of non-polyoxometalates that's called kaolin. In the center, we have heteroatom that it can be phosphor or silicon, and around that we have 12 units of metal oxo that have 6 oxygen each one. So what is unique in this family that first it has variety of structures, redox activities, solubility that will open the door for homogeneous catalysis, of course, stability, and easy synthesis for abundant metals. Specific in my project, we took a family of lacunar polyoxometalates, and how we got that? This family produced by removal one or more metal oxo units of Kegin. So if we, for example, remove one unit, we will get the monolacunary structure. And if we remove 3 units, we will get the trilacunary structure. And in this trilacunary structures, we have 2 isomers. The first one is called A type, and that means that the units of metallo-oxo is corner shared. And the second isomer is the B type, and that means that the metal-oxo is edge shared. And what is important here, and I want you to remember that the formation of each one of them is mainly pH dependent. That means if, for example, if I want to synthesize trilacunary structure, it must be in basic pH equal more or less to none. So in our project, we first synthesized the trilacunary and we substituted that with different first row transition metals such as copper, iron, nickel, and their combinations. And we check the electrochemistry by using first the undivided cell that includes 3 different electrodes. We use glassy carbon as working electrode, platinum wire separated by glass frit as counter electrode, and ferrocenium plus as reference electrode. And in some stage in the project, we use the divided cell that include 2 electrodes that are separated between them with a Nephron membrane. The first electrode is titanium electrode as a working electrode, and the second electrode is carbon cloth as counter electrode. So we succeed to synthesize all the catalysts with all the combinations of copper, nickel, iron. And in order to be sure that we did that in the right way, we characterize that by 2 methods. The first method was IR, and the second was high resolution MS. The IR helped us to be sure that we have really the trilacunary, and the high resolution MS help us to be sure that we have exactly the ratio between the metal that we put inside. And then we start to measure the electrochemistry properties of these interesting complexes. And I will present you here just 2 complexes, the copper 3 and iron nickel 2. And so what is important here, when we try to measure CV for that, you can see that when we try to add carbon dioxide to the complex, we immediately see increasing current. That means that we have catalytic current that indicates that we have catalysis here. And the same things is also in the iron nickel complex. And when we try to calculate the turnover frequency from the CVs, according to the known equation of theoretical turnover frequency, we got 1077 second minus 1 turnover frequency of copper 3, comparing with less turnover frequency of iron nickel 2 that equal to 183. And in this moment, we continue and think to calculate the catalytic Tafel plot of the different complexes in order to understand the difference between them. And as we know, catalytic Tafel plot is compared between different complexes in their intrinsic properties, and it's independent from the experimental conditions such as cell geometry. And what is important for me to tell you that a good electrocatalyst is defined to have high turnover frequency, low overpotential, and high stability. And in our results, what we got, first, that the slopes between the different complexes are more or less the same, are similar. But the interesting point here that is significantly lower overpotential required for CO2 reduction with the copper 3 catalyst. So you can see here that it's significantly lower. So from this point, we decided to check the reaction. So we go to our undivided cell, we bubble CO2, and we check the product that we got with both catalysts. And if we compare the copper 3 catalyst and the iron nickel 2, you can see that we got very beautiful amount of CO with the copper 3. It's equal to 24 micromole of CO with 98% Faradic efficiency. But when we try to measure the product in the iron nickel 2 complex, we got very few amounts of CO. And that was a little strange to us because also in this complex we had a catalytic peak. So where are the products? So that gives us to think about non-family of enzymes that known in the literature that called the carbon monoxide dehydrogenase enzyme. This family are biological catalysts for reversible oxidation of CO to CO2 with water as the source of oxygen. And you can see here that the oxidation of CO to CO2 is much faster than that reduction from CO2 to CO. There are two types of this family. The first type include nickel and iron in their catalytic center, and the second type include copper, molybdenum, and iron in their catalytic center. So in this moment, we thought maybe our iron nickel complexes, what happened there, we produce the CO and immediately we oxidize that to CO2. So because of that, we didn't see any product. So in order to check that, we did the reaction in both reaction, the forward and the reverse reaction, and we compare that with the different combinations. And as you can see here in this result, you can see that the forward rate reaction is the highest we have with copper 3. And when we start to add iron and nickel, it reduced the forward reaction. But if you look to the iron nickel family, you have strong reverse reaction. That means that all the CO that we produce immediately, we have it as CO2 as product. So that's very nice because it gives us to thought that we can control by changing the metal, the rate of the reaction. And in this point, we go inside the mechanism in order to understand how the mechanism of all the complexes work with the reduction of CO2. And we check the mechanism in situ by measuring in situ electrochemical measurements using UV, IR, and Raman. I will present you UV and Raman today. So as you can see in the UV result, first with nitrogen, before reduction, we have the LMCT peak, the non-peak of large metal charge transfer of the oxygen of the foam toward the metal of the catalyst. And you can see that when we start to reduce that under nitrogen, we have immediately the Young-Taylor effect. That means that we have mix of copper. We have copper 1 that reduced from copper 2, and we have also copper 2. And then when we start to add CO2 or CO, we have oxidized back the metal again, and that means that we have some binding between the CO2 or CO with our catalyst. In the iron nickel 2, we have more or less the same phenomena, but it's less strong. When we try to measure in situ Raman during
2 minutes.
When we try to measure in situ Raman during electrolysis, and this measuring done by with collaboration with Dr. Charlotte Vogt, we measured that by using a cuvette with 3 electrodes, as you can see here in the picture, and we saw that we got with the copper 3, we got species of CO that disappear in iron nickel 2. That means that we have this species here, and in the iron nickel 2, that is the reverse catalyst, it's as expected, we don't have it. Another peak that we got is this peak that is not appear in copper 3, and it's may related to CO2 minus species, but we are not sure about that. So we can conclude and say that we prepare a series of catalyst that of trilacunary structure that substituted with first row transition metal of iron, nickel, and copper. Catalytic Tafel plots showed that the copper-3 catalyst required the lowest over potential, that is the lowest kinetic energy barrier for catalysis. In the copper-3 complexes, we showed a significant catalytic peak in the CV, and in the electrolysis for after 15 hours at minus 2.5 volt, we obtained 24 micromole of CO with 238 of turnover frequency and 98% of paratic efficiency. And this is likely the best result recorded for molecular copper compound in the literature. These catalysts are functional models of carbon monoxide dehydrogenase enzyme that contain iron and nickel atom at their active site. And finally, mechanistic studies using Raman spectroscopy show observation of species of copper CO intermediate formed in the reaction of copper-3. So I want to thank to my advisor, Professor Ronnie Neumann, and to my excellent group members. Thank you. Thank you. So.
Okay, thanks, Dima. This was a very nice presentation, very nice talk. Someone has any questions? No? So I have a few questions actually. First of all, about regarding the synthesis of your catalyst. So you actually said you removed the units from the structure, right? And you characterized it using methods that confirm that you indeed have the groups and you indeed have the right ratio, right? But how did you confirm that you have the 3D structure?
Again,
how did you confirm that you have really the structure that you have drawn in the presentation?
You mean XRD structure or something?
Yeah,
like
or
that?
something.
Yeah,
mm-hmm.
yeah. It's a good question. It's hard to crystallize this structure. It's so hard because the structure that I have has organic cation, and it's hard to crystallize that. It's so amorphic structure. But we continue working on that, maybe to use the potassium salt one in order to have it. But I think that high resolution MS of that it was very unique measurement.
So Dima, I think you are stuck. Is it my internet connection? Can you still hear me?
Yeah, specifically to the trilacunary structure.
Sorry, can you repeat your last sentence? I think you lost the connection.
So yeah, I think the combination between the MS and the IR give us to be sure first that we are in the right structures, but I can understand you that it's not enough picture to make sure that it's the real crystals. We need the crystals for that. For this moment, it's enough for us, the IR and the mass spectra. Yeah.
Okay. And did you study the stability of the catalyst for various catalytic cycles? For example, did you repeat the IR and the MS measurements after the catalysis?
Yeah, of course, I did that, and it's so stable. It's we have a very strong stability.
Okay. Last question. Can you please go back to the electrochemical characterization? Maybe I didn't understand something in the graph. To the CV, to the cyclic voltammetry.
Cyclic voltammetry, yeah.
Yeah. So in the right graph, how do you know it's really a catalytic peak and not the solvent breakdown? I'm sorry for my question, but...
Yeah, no, it's a very nice question. A solvent increasing current, it's much more higher. It's very
Okay,
higher current
I can
comparing
see
what
now.
we got.
I can see now the
Yeah.
I think, but
Yeah.
like if you repeat it, my advice is to maybe widen the scan range so it will look like a peak and nobody will confuse it with the solvent.
Yeah,
Okay.
yeah. But comparing with the solvent, it's much more higher.
Yeah. I now see the orders of magnitude of the yeah. Okay.
Exactly.
Thank you. Sorry for my sorry for all the questions, but it was a very
No, it's okay.
Okay. Thank you, Dima. Our next speaker is Melina. Melina from Bar-Ilan University. Okay, Melina, so you have 15 minutes as well. So good luck.
Can you see what I'm showing now? Is it in?
Yes, we can see
now in the presentation. So, hello, I'm Melina from Bar-Ilan University, from David Seitun's lab. And today I will present a project that is called Carbon-Supported Platinum-Nickel Octahedral Electrocatalyst as a model to follow nickel corrosion and particle detachment. This is a collaboration with the INL, with Portugal, the Nano Center there. So today in the street, we can start seeing some electrical vehicles. We have some Teslas in Israel also. And I promise that this talk is not sponsored, but here I have the Toyota Mirai. It's one of the electrical vehicles that are based on fuel cells. And as you can see, there are not a lot in the street yet, but one of the reasons is because of the cost. You can see that in the United States costs between 60 and 70,000. And for cars with these characteristics, usually you can find cheaper. So let's see why this car is so expensive and how it's working. So here you have inside a fuel cell. Inside you have also a hydrogen tank, and you have batteries and electrical motor. So the good thing of these cars is that there are not emissions, like the previous lecturers said. In this car, the main reactions in the proton exchange membrane fuel cell, the electrochemical device that converts hydrogen and oxygen, produce only water, electrical power, and heat. So this is really good. This is environmentally friendly. So the bad thing about this is that the ORR is the oxygen reduction reaction. This needs a catalyst because the reaction is very slow. So usually the catalysts are based on platinum. There are nanoparticles based on platinum that are in different kind of support. And platinum is not abundant and it's very expensive. It's a precious material. So imagine that each of the cars here have between 3 and 8 grams of platinum per car. Toyota Mirai report that they are using the platinum cobalt alloy. So first of all, there is not enough platinum in the world for all the cars that will be produced in the future, and also will be very expensive. So the goal here is to create a good catalyst that will have a good performance, that highest efficiency, and also to reduce always the content of precious material. The precious material, it's not only the platinum, but platinum group metal, that means iridium, palladium, that today they are even more expensive than the platinum. So this work relatively simple. In oxygen, it's coming to the surface of the catalyst, and the oxygen molecule divide. And then because we are in acidic condition, it creates water. So this is the good thing. Usually the particles are supported in, for example, carbon, but there are thousands of different supports. So what was the evolution and what are the challenges that we have with this kind of cathodic catalyst? The beginning of the 90s was study the mechanism, what I showed you before, and not only the main pathway, but all the different pathways and different products that can be produced. And was study the use of the Naphion. Naphion is the ionomer. It's also used in the membrane for the fuel cell, and was only connected, all the study was focused on the single metal. the shape of the platinum particle, the size of the platinum particle, the loading of the platinum that is needed, but only based on platinum. Then, with a study of the volcano plots, was found that if the platinum is combined with transitions metal like cobalt, nickel, copper, even iron, the activity can be enhanced, so it can be improved the catalytic activity. And all the studies were based on how to create the alloy, what will be the composition, how to de-alloy this particle, how to create core shell, how to make platinum skin, or how to create different hollow particles. So this was the second study. The last decade was based on the shape control, like all what we know about the bimetallic particles, how to control the shape. Why? All these electrochemical reactions occur in the surface of the particle. So if I have different shape, I will have a different activity. And in this moment is when the cars appear, because it can be controlled, the loading of platinum, the composition, the shape, and this is enough to start producing the first car. So the question is what we do now, what is the challenge for the next decade? And the challenge for the next decade and what we are working, it's in the durability of this catalyst, because the massive production will be possible if this catalyst lasts at least years. Yes, like that we can prove that the catalyst will last as much as possible. So what we do in our lab is to study the relationship between the synthesis of the particles, the performance that we obtain, and how this influences the stability of them. So connected with the synthesis and the performance, we have different works that were published in the last time, connected with how the shape influences the ORR, how the size depends, modify the ORR, or how to create skins, platinum skins, core shell, core bishell, and more. Once we have a good material that usually is platinum based in copper, we study the stability. We perform 10,000 cycles, even more, 20, 30, depend of what usually the parameters that compare between all around the world. We study how will be the performance after, for example, 10,000 cycles. But what I'm going to show you today is that we can understand some things about the stability, not to performing the electrochemical measurements, because it, first of all, takes time, takes a lot of material, and it's not always so simple to do it. So how we can understand the structure, and because of this, to know some properties about the stability based on the platinum nickel nanoparticles. So why it's important to understand the stability and what is the degradation process that can happen? If the particle or the catalyst has degradation process, the activity will decrease and will be destroyed, and it's not useful for research nor useful for the industry. So some problems can happen in the support, could be corrosion of the carbon, could be poisoning here, could be also the problem, the degradation of the particles. So usually if we use nickel or copper, the transition metal leach, and this is very common problem, but also coarsening or collapse the particle. And also we can study all of those are some samples that we work in different projects in our lab. And also the particles can detach. And this is one of the worst. If the particles leave the support that you have inside the fuel cell, the catalytic activity will disappear completely. So how we study this degradation process? So the simplest one is to compare beginning of life and end of life. We analyze the activity before and after, and we look at the images if the catalyst looks similar. The second option that we are doing more in the last few years is identical equation TEM. So we track specific particle, a specific region after different treatment. So we can see here, not only if the particle has the same shape or if there are leachings, but we can see if they're coarsening, if there is some modification in the support, We can see if there is coarsening, how many particles disappear between one treatment and the other. So this is provide us more information. And this is how we do it. We use specific grids for TEM, and then we cycle everything there. So all the electrochemical information that we take from this identical location is exactly the same as when we perform the electrodes. And this is the less use, but provides more information. That is our collaboration group from Paulo Ferreira. You can follow inside the microscope the structure and the change, and you can see even smaller changes. This is when you heat the catalyst, platinum catalyst on carbon support. So all this is the classical way to understand degradation. And you need materials, and you need a lot of different requirements, and takes a lot of time. But this is another approach that I want to show you, that you don't need always to reproduce exactly all the environmental conditions of the electrochemistry. But if you know what is the condition or what is exactly problem that you want to study, you can obtain a lot of information of the structure of your particle, or if your catalyst will be useful, analyzing in a different system. So what's the system that we analyze is the degradation products from the proton exchange membrane fuel cell. So the degradation products that have contact with our catalyst. Not only the catalyst degrade, but all the components of the fuel cell usually degrade after using. So this is the Nafion membrane, is the most common use, or if it's not Nafion, it's the family of the Nafion. And the degradation products usually are carboxylic acids. So these carboxylic acids are the products of radical substitution. And we have a lot of radicals inside the fuel cell, because nickel, the second metal in the catalyst, activate the formation of peroxide. So this is a very common product to obtain to have carboxylic acid inside. So what we want to know specifically is how carboxylic acids or other type of groups, like similar acidic or even not so acidic, will influence the stability of octaedral platinum nickel nanoparticles. So what we have here is a two-phase corrosion process system. We have the particles suspended in the organic phase, and in the aqueous phase, we have a cleansing agent. This is an agent that traps the nickel, that have a very high affinity to the nickel. And these cleansing agents contains the organic groups, for example, the carboxylic acid. So we can see how in the environment of the carboxylic acid and others environment more, this particle will change the morphology. Initially octaedral, because it's the one that was optimized for this type of catalyst, and how we look in the end. And I will spoil you a little bit, but the important thing is depend of the groups, the organic group that you have here, depend of the chemistry, will detach the particles or not detach the particles, and we will see now here. So we start with platinum nickel particles, very common, standard size, standard composition, something that is used, and we know the activity. And we expose to different chelating agents with different affinity for the nickel. We try with different organic groups, with more basic, with more acidic, and we tested, as I said, in the two phase. What we obtain, half of the chelating agents keep attached the particles, and half of the other ones detach the particles. And all of them are corroded. All of them were octaedral in the beginning, and they are concave in the end. So first of all, the composition of the particle will change, and if very dangerous, if nickels goes out from the particles, not only decrease the activity, but also it's creating poisoning all around. And the size also changed a little bit, not so much. So we wanted to know why some cleansing agents detach the particles and why others not. The first thing is to think about the pH. We can suppose that acidic pH, we leach the particles, we leach the nickel and remove the particles, but not. If you see the similar pH can detach or attach. So pH is not the problem. Then we check the affinity of the different decalenting agents to the nickel, and it's not also the affinity. So in the end, we found that it's the ratio between the oxygen and nitrogen, like the amount of carboxylic and the amount of amines that has the decalenting agent, that removes or not the particles. And this is very important. So if you have amines that come from nitrogen dope carbon support, or if you have any kind of amines, this will be very dangerous for your particles and for your catalyst, and that means that it's not useful for your fuel cell. So I will skip this, maybe. It's what happened with the particles have a different composition, and with high composition, rich composition in nickel, you will obtain hexapods that are really important and really interesting also for the catalytic activity. I will close here because I'm on time, so this is the summary. If you have platinum and nickel particles and you have interaction with amine groups, the particles will detach and will be terrible for your catalyst. If you have carboxylic group, it's not that important. You will have leaching and concavities, but the particles will stay there. But if you have a very rich in nickel particles, you will create hexapods that have very interesting geometry for the activity. So I would like to thank everybody in my group, especially to Tal, Sam, and Victor, that they are part of these projects, and the collaboration with the INL, Paulo Ferreira, Charles Amos, and Enrique Carboar Gibay. So thank you for your attention too.
Okay, thanks, Melina, and thanks for sticking to the schedule. Does anyone has any question? Okay, so I will ask.
Yes.
Okay, so in the first part of your research, actually, I have a question that is applies both to the first part that you presented and the second one. So in the first part, you presented like the normal characterizations for stability, right? For
Yes.
example, multiple cycles and the heating. So I wanted to ask you if you think those characterizations are really applicable for real fuel cells inside cars.
Yes, what I show is what we do in our lab. It's the RDE step. The RDE is when you test an electrode, but exactly the same you can do with the fuel cells. Like there are groups that they build, we build, but not all that kind of fuel cells. And yes, what you do is to remove, open, measure, and come back. It's the closest that you have. You cannot always measure in situ, like you cannot measure in situ a fuel cell, but yes, you can measure in situ the catalyst. If the connection between, there are a lot of samples that are good in the lab, but not in the real fuel cell. This is a big problem.
Yeah, that's what I asked.
Yes, also the opposite. Sometimes we are so concentrated looking for exactly perfect shape and a perfect distribution, but we found that particles that are less homogeneous and less like pretty design, they are even better performance. So, but if we don't do the first characterization in the lab, and if we don't analyze the degradation, and if there are thousands of particles that are created and only few reach the fuel cell, usually. You have one good candidate between a lot of them. So it will be very difficult to test everything.
Understand. So you just do the initial testing in your lab.
Yes.
And in the TEM, just from curiosity, to what temperature did you, in the in situ TEM, to what temperature did you heat it?
This is not this is the only picture that is in not our lab, but they heat between 200 and 500.
Ah, okay. I didn't know it's possible.
Yes, it's possible also to do the electrochemical reaction inside the microscope today with gases and liquid also.
That's interesting. And last question applies to the second part of your research regarding the chelating agents and the ratio between the nitrogen and the oxygen. So if I understood you right, so the nitrogen to the oxygen to nitrogen ratio is the main parameter that affects the stability. And I think you said, I don't know if I understood you right, that it can be applicable also to if you, for example, dope your support or something with nitrogen or oxygen, right?
Yes, yes. A lot of ways to enhance activity for the catalyst are usually to treat the particle and the support in the same time. So nickel.
My question is that okay, you found this. You have this conclusion for the chelating agent specifically, but how do you know it's also right for the doping?
Well, we don't know exactly if it's right for the doping, but the idea is to consider that if you dope with nitrogen or if you have different nitrogen groups inside your support, maybe this will detach your particles. So
okay, it's not something you actually tested. Okay.
No, because for this we need to dope the carbon and to test exactly the difference, the same particle, dope and not dope.
Okay. Okay, so our time is out. So now we have, thank you, Melina. It was a really, really great talk and great presentation. Now we'll have 10 minutes break, and afterwards we'll have the roundtable discussions with the representatives of the different companies. So see you.